At the minimum for our game, we need to be able to draw pictures and to consume user input. Let's look at the basic drawing functionality of LibGDX and basic input processing of LibGDX. What exactly is LibGDX? It's a platform-independent programming framework, which is written in Java, and its independence is provided by having a generic application interface that provides certain functions, certain methods, and then having platform-specific implementations of this application for all the different platforms supported. When we write a program using LibGDX, we use different classes from GDX package. And GDX package has several static objects as part of it that provide programmer access to big chunks of LibGDX functionality. So if you write in your program gdx.app, that's a reference to the application that's currently running. And if you are on the desktop, it would be LWGL3 application instance. Now, in addition, gdx.graphics provides access to all the functionality for drawing things in the game window. gdx.audio provides methods for recording and playing back audio through the sound system. gdx.input deals with user input, and because it's a cross-platform framework, it provides methods for handling mouse movements, gestures, and keyboard inputs and the like. Sometimes the same touch functionality is used for mouse clicks when there is no touch screen, or for actual finger touches when your game plays on Android, for example. gdx.files provides access to the file system, so we can access files from within jar file, from the external file system, and so on. And gdx.net provides methods for accessing network resources, making HTTP requests, creating server and client sockets, and so on. When we create a LibGDX application, we basically create an instance of LWJGL3 application object, and to this object we give our instance of our game object that we create, and we give it an instance of the config object. Config object is paired with platform-specific application. So for LWJGL3 application, we need to create application configuration object. And we can call methods on this configuration object to specify certain properties of our application. For example, we can set window title to example 1. We can set dimensions of the window, 600 by 400. We can specify whether it's resizable or not resizable. And there is a host of other configuration parameters that we can change. Obviously, explore and use as you see fit. Inside the application, the first thing that we use is graphics, because ultimately graphics is what the games are about. When we want to draw something with LibGDX graphics, it uses graphics card as the backend, which means that we need to take all the pictures we want to display, all the instructions of how we want to display them, and send them from CPU into the graphics card. Let graphics card do its job and receive back the picture which we display to the user. Because of that, drawing in LibGDX is done in batches. LibGDX defines special interface called batch and several implementations of which. The most commonly used one is called SpriteBatch, that provides a way to draw images all over the world plane. So we need to create an instance of this SpriteBatch. That's our interface to the graphics hardware. Next, we need to create a texture. And texture is basically an image. LibGDX provides several variations of these texture objects. In the simplest case, picture is the texture, and we draw it as is. Now, in LibGDX, we have also a thing called a texture atlas, which is basically a big image, the regions of which can be drawn as independent pictures by SpriteBatch. And then we have multiple applications of this texture atlas. For example, if we want to display a string of text, we can take pictures of individual letters and digits, put them in a texture, identify regions for each of the letters, and then create a special class, which in LibGDX called bitmap font, that will have a method to display a line of text. So we give a text string, the coordinates, and it pulls pictures of individual letters, puts them in a line as requested, and displays them as a composite picture of the text. In essence, we have a SpriteBatch. That's the interface to the graphical hardware. We have texture, which is a picture. And we also need special object called camera. Cameras are needed because drawing is done in 3D space. And our window is obviously two-dimensional. And we need a way to display a fragment of this 3D space, of whatever we've drawn in 3D space, in a window. So how is this done? The transformation is a little bit obscure, and I've shared it with you link to YouTube lecture by Ken Joy from UC Davis. It's 47 minutes that goes in some detail about how these cameras in 3D graphics work. I welcome you to listen to that lecture. It's optional. It's not necessary, but for your own information, it's useful to get at least the general idea of what's being done and how. Camera is basically a matrix, combined matrix, camera.combined, that describes a mathematical transformation that needs to be performed on three-dimensional points to bring them to this two-dimensional space of the screen. Okay, so now how does the drawing proceeds? First, we configure our camera to be at a specific location, to look at a particular portion of our world, and we give this configuration to the SpriteBatch. After this, we say, SpriteBatch, let's begin. After this, we perform several draw operations, or rather we describe several draw operations, which basically say where and how we want to display our texture or fragments of our texture. And we can do tens of thousands of these draw instructions in one go. And then we say end. And when we say end, the texture and all of the drawing operations are communicated by the CPU to the graphics card, and the actual drawing is performed. So when we perform a single batch draw, it takes quite a bit of resources to communicate everything from CPU to the graphics card. But once the data is in the graphics card, the processing happens very fast. So with a single batch draw, we can draw maybe tens or hundreds of thousands of images of this texture or its fragments in one go, and it will be fast. But if we have to do multiple batch draws very often, it might be costly from a resources perspective. So the most basic example of the program looks like this. And I have created a sample project. So I'm just going to start it, and let us explore it. The very basic application only has a render method that clears the screen. And that's the absolute minimum functionality of the LibGDX that we can have. It will display just a blank screen of a certain color. So suppose I want to display a picture on this blank screen. How do I do this? First of all, I need something to display. On the internet, I found a free image, changed it to certain dimensions. And here in the image size, I can specify how many pixels I actually want it to be. So 200 by 200 and export, replace. So out of a scalable vector graphics image, which I can reduce or compress without loss of quality, I got an image like this. A PNG file I can display. Now observe that PNG file has certain pixels which are transparent. So we have kind of image itself that's white, black, blue, and here we have area which is transparent. So I've taken this image and I've dropped it into resources folder of my project here. So in the resources, I have this hacker PNG file, which I'm going to display. So now I've expanded my basic render method to have a few more things. So first I created several fields. One is called texture to hold the PNG image, an instance of SpriteBatch to do the drawing, and an instance of camera to specify which part of the world I want to look at. Now I've added create method. So when our application is first created, this method is called, and that's the place where we can load stuff from files, for instance. So here I create my objects. I create a texture object, and as a source of it, I give it a path to hacker.png file inside my jar file. So internal here specifies that this file is to be taken from inside the jar file. If it was external, it would go into the file system. I create an instance of SpriteBatch, and I create an instance of orthographic camera. Texture and SpriteBatch have elements tied to the graphics card. And because they're tied to the graphics card, we need to call dispose methods on them. And now in my render method, the first thing I do, I configure my camera. So what I do, I call method called set to ortho. And it takes 3 parameters. First is Boolean, which tells whether y-axis of the world points up or down. By default, it points down. And here, by specifying false, I tell that the y-axis of the world plane points up. And here I specify which portion of the world I want to display in the game window. So GDX graphics get width gives me the width of window in pixels, and GDX graphics get height gives me the height of the window in pixels. I configure it to look at the world plane and to display in my window as many pixels as there are pixels in the window. After any configuration of the camera, I need to call update so that all the settings that I have specified are compounded into a single 4x4 matrix, which is then used to perform projection from the 3D space into 2D space. Next, I set projection matrix of the SpriteBatch to be that camera.combined. And that's camera.combined is the 4x4 matrix that incorporates all of the configuration changes we made here. So now our SpriteBatch knows what portion of the world we want to display in the window, and we are ready to draw. So we do batch begin, and then we say draw hacker picture at the origin, x equals 0, y equals 0. And by saying end, we send all this information to the graphics card and get it to draw the picture for us. So let's see what it looks like. Building it. I am still building it. Okay, I'm compiling and building shadow jar, and now I am going to run it. Okay. So what we see here is a picture of our hacker displayed in the bottom left corner of our window. Remember that our window is 600 points by 400 points. And when we perform call to this set to ortho, it shows us region of the world plane from 0, 0 to whatever dimensions we specify. And that's what we see in this screen. What happens if I resize the window? Well, let's check it out. Remember that it redraws, it calls this render method a few times per second, not just once per second, but maybe 10, 20 times per second. So every time it goes here, it gets current dimensions of the window and changes the display to match the current size of the window, updates the camera, and communicates amended projection matrix to the batch and then redraws it again. So in effect, what we see here is different portions of the world plane. We can choose to display twice the size of my window. What will happen in this case? It means that twice the dimension of the window need to be fit into the window. So if I rebuild it and if I rerun it, suddenly the picture of my hacker got smaller. Why is that? Let me change this viewport remove curing of the window parameters and just set my camera to constantly point and display fragment of 600 by 400. And if I rebuild it and then rerun it, this is what I get. This is our original picture because 600 by 400 is the original dimensions of this window. Because now my camera viewport widths and heights are fixed, see what happens now when I resize the window. Camera stretches to match the window. So basically, camera describes which portion of the world has to fit in my window. And by specifying this configuration here, I say, camera, display to me a rectangle from the world plane, 600 by 400. And here I have 600 points horizontally and 400 points vertically. And because I don't modify parameters of my camera now, because they're fixed, when I reduce or stretch, each point is reduced or stretched accordingly. So camera describes what portion of the world is displayed in the entire window. And this is kind of important. Now I say 120 by 800. It will get smaller because now on the screen, I have not 600 by 400, but I have 1200 by 800. So I simply display bigger portion of the screen in the window. And because window stays the same size, obviously everything gets smaller to fit in. Now, this is single draw operation. What if I do this? What if I take this and choose 300 by 200? What if I do second batch draw on the same screen after the first draw, and I specify different resolution of the camera? And that'll be the last thing we cover today. Like this. So interesting thing happened. We performed 2 draw operations. The first draw operation, 1200 by 800, created this little guy at the bottom. The second draw operation, we zoomed camera in and redraw the same picture at exactly the same coordinates. But it became bigger because now our camera is closer. What does it tell us about the way batch draws work? Are you familiar with the thing called lomography? It's when you take a camera and you take several exposures on the same film, and different images go on top of each other. And that's exactly what happens here. When we perform draws with different camera configurations, the draw is performed, the snapshot according to the camera is taken, and then all of them go on top of each other. They're all compounded, and that's what we see. Thank you very much for your attention. Next week, we'll continue with some advanced drawing and input handling.